Hi everyone, this is Chao Li from City University of Hong Kong. I'm going to share our work, Shaping Retries with Sentinels for fast read over high-density 3D flash. I will present our work from the following 5 parts. First is some background and related work, then some observations and analysis. Next is our proposed Sentinel-based approaches. Finally, its experiments and the conclusions of this work. Nowadays, NAND flash memory has been adopted in various storage systems like mobile, computer, and servers due to its high performance. Based on the number of bits stored in each cell, NAND flash memory is grouped into several types. In this slide, we use TLC flash as an example where each cell stores 3 bits. The figure shows the threshold voltage distribution of TLC. There are 7 read voltages to differentiate 8 voltage states. In NAND flash memory, different types of error sources impact its reliability, like disturbed retention loss, PE cycles, and layer-to-layer variations. The threshold voltage in one state may shift to other states, which introduces errors on the stored data. Because of the voltage shifts, the RBR heavily depends on the value of the read voltage. There exists one optimal value that will introduce the lowest RBR. For example, when the voltage states shift to the left, we can reduce the RBR if we tune the read voltage to the left at a proper offset. Retry operations are introduced in NAND flash memory to realize the function of voltage tuning. Then we introduce some existing methods to find the optimal read voltage. One method employs a binary search algorithm which tracks the ratio of zeros and ones for each read voltage it tries. The binary search algorithm continues narrowing down the range until it finds a read voltage that satisfies the ratio. This method will result in an unpredictable number of read retries. Another method records the key information like the number of PE cycles, retention time, and exit. And then they develop a model of the optimal read voltage. Based on the model, the read voltage will be predicted. For this method, it requires large overheads to record the information. Besides, there are more types of errors on 3D NAND flash memory. It is very challenging to accurately predict the optimal read voltages. To obtain the optimal read voltage, we begin with characterizing the RBR and the optimal read voltages of high-density 3D NAND flash memory. The figure shows the RBR of TLC and QLC flash. The solid lines shows the RBR when reading data with default read voltage, while the dashed lines show the RBR when using optimal read voltages. We can observe that first, reading data with the optimal read voltages significantly reduces the RBR, especially for QLC flash because there are more errors. Second, when using the default read voltages, the RBR presents huge variations among layers. But if we use optimal read voltages, the variations of RBR among layers can be reduced. We then study the temperature effects on high-density 3D flash memory by placing the flash chips at the room temperature and at a running computer case for an hour. These two cases are possible working environments of flash memory chips. Compared with the room temperature, the RBRs of the chips in the computer case are higher, and the optimal values are different. The reason is that high temperatures in the running computer case can accelerate the rotation effects of flash memory. The result indicates that the optimal read voltages may change in a short period of time if the working temperature is high. which raises further challenges to predict the optimal read voltages. We then present the positions of error cells inside one block of the evaluated flash chips. In the figure, each blue dot represents a cell that has an bit error. The dark and light horizontal stripes show that the RBR varies greatly among different word lines. Therefore, the error characteristic of one word line cannot represent the error characteristics of other word lines inside the same block. However, the errors are almost uniformly distributed along a word line. This is because the main shift due to the error sources, including the P cycle retention time and the temperature, is global for all the cells on the word line. They have endured the same error sources. Therefore, the errors of a small set of cells can predict the errors on this word line. In this work, we propose to reserve a small subset of cells on each word line as sentinel cells. We then study the correlations among the values of optimal read voltages. V8, the read voltage, to differentiate the 7th and the 8th program states of QLC is used as the example to show the relationship. As the figure shows, the optimal value of every read voltage shows a linear relationship with the optimal value of V8. And also other pairs of optimal read voltages also present a linear relationship. This relationship indicates that once the optimal value of one read voltage, for example V8 in this figure, is achieved, we can infer the optimal value of other read voltages. This property leads to the option of picking one read voltage as the sentinel voltage and relieves the need to track all the read voltages. To minimize the number of retries, we propose to directly infer the optimal read voltages with sentinel cells and the sentinel voltage. This work uses V4 as the sentinel voltage for TLC and V8 as the sentinel voltage for QLC. During write operations, sentinel cells will be evenly programmed to the two voltage states between which the sentinel voltage lies. For example, S3 and S4 for the TLC. And during read operation, we can count the number of bit errors on sentinel cells by comparing the original data and readout data, because we already know the original data we programmed on the sentinel cells. Therefore, the optimal value of the sentinel voltage can be inferred. We use the error difference to infer the optimal read voltage. Error difference is defined as the difference between up errors and down errors. Up errors are errors resulting from the cells in the left voltage state being misread as the right voltage state, and down errors are the errors resulting from the cells in the right state but being misread as the left state. By collecting hundreds of pairs of the error difference and the optimal voltage, we use polynomial function to fit the relationship between the two. The left figure shows the fit result, where the relationship is well fitted as the polynomial function of degree 5. And the right figure shows the predicted optimal value of read voltages. The inferred value is equal to or very close to the real value of the optimal read voltages for most cases. However, a small part of word lines cannot obtain the optimal value from the inference. The reason is that for these word lines, sentinel cells cannot exactly represent the whole word line. There are some difference between the sentinel cells and all the cells. We consider two cases. First, the inferred tuning offset is smaller than the real optimal offset, and the read voltage should be tuned more in the same direction. And second, the inferred tuning value is greater than the real optimal value, and the rate voltage should be tuned back a little bit. So from the figure, we can see that the cells with state changed in case 1 are closer to the mean of the distribution. So with the same distance, the integral of the areas of case 1 between the inferred voltage and the default voltage is supposed to be larger than case 2. We validate the relationship with the comparison of the number of state change cells by changing the position of the area. The numbers in the legend represent the position offset to the real optimal rate voltage. The positive atoms in the legend represent case 1 and negative atoms represent case 2. The results show that the average number of case 2 is greater than that of case 1, which validates the relationship of the two cases. So we can, based on the relationship, to tune the optimal value after the failure of the inference. Our evaluations are conducted on Easter SSD testing platform. Both TLC and QLC flash chips are evaluated. In default, the percentage of Sentinel cells is set as 0.2%. First, we show the accuracy of finding the optimal rate voltages. After inference, more than 83% of wire lines can obtain the optimal value of rate voltages, and after calibration, 11% more wire lines can obtain the optimal value. Next, we compare the number of retries. Compared with current flash, they already implement some optimization method. Our proposed approach can reduce the number of retry by 82%. We then show the improvement on the read latency. The proposed approach can reduce read latency by 84%, 74% on average. The main overhead of the proposed approach is the space taken by Sentinel cells. We use the evaluated flash chips as an example. The page size of the flash chip is 18,000 and something bytes. The space to store user data is 16 kilobytes, and the OOB space is about 11% of the total space, and ECC parity takes more than 10%. So that leaves 192 bytes available for Sentinel cells, which is much greater than our value 0.2%. This means there is low loss in the space. We still consider the worst case. What if the Sentinel cells take up the space of ECC parity? The figure shows the comparison of the ECC capability. The proposed approach leads to a marginal loss in error correction capability, which can be well compensated by the improved read performance. Finally, it's the conclusion of this work. On high-density 3D flash, there are multiple types of errors, which makes it hard to find the optimal value of rate voltages. In this work, we propose to reserve a small subset of cells on each wire line as Sentinel cells and one Sentinel voltage. We infer the optimal value of rate voltages based on Sentinel cells and then collaborate the optimal value after failure of inference. And finally, we validate the effectiveness of the proposed approach. Thanks for your attention. If you have any questions, welcome to my session.